So we're going to start this module by going over some basic chemical vocabulary and chemical principles. So for all the videos I'll be showing, I'll start off with these kind of summary slides, and you'll see them again at the end. As you're watching, these are things to pay special attention to, and as you're studying for tests, I would come back to these because these will be sort of a good idea about what to focus on, what's really important here. So for instance, in this video, we'll define elements, atoms, molecules, and ions. These are key terms that we'll keep coming back to throughout the semester. We'll also describe how the periodic table, the organization of the elements, is set up and what kind of chemical information that really tells us. We'll also use the periodic table to predict how different chemicals, different elements can bond together through covalent and ionic bonds. We'll also look how interactions between molecules can dictate different states of matter, like solids, liquids, and gases. So this is a periodic table. You've probably seen it before. This is a list or compilation of all of the known elements in the universe, most of which occur here on Earth, and most of which are found in the oceans to some degree. So what we'll do at the start of this course is basically talk about how each of these elements were made in broad strokes, and how that sets up the unique conditions for Earth and the solar system, and how that influences the oceans as we know them today. So for some basic terminology, an element is a pure substance that can't be broken down further by chemistry. And this is sort of the origin of different properties. So for instance, iron is an element, and beams made of iron are used in buildings because they're very rigid and solid. You can trace those properties down to the elemental properties of iron itself. So the smallest unit of iron or any other element is called an atom. Atoms have a nucleus and an outer shell and electrons, and are basically identical. So all iron atoms are the same. So atoms can bind together to form molecules. So some of these you know already, like oxygen, water, H2O, is hydrogen and oxygen bonded together. Here's iron oxide, so Fe2O3. There's 2 irons here and 3 oxygens bonded together. And this one's harder. This is glucose, sugar, C6H12O6. So molecules are more than one atom that are bonded together. So another term we'll see a lot are ions. So ions can be atoms or molecules that have positive or negative charges associated with them. This really influences their behavior. So if you dig into the structure of an atom, what you'll find is a nucleus, this core here, that contains neutrons and protons. So neutrons have mass, but they don't have any charge, versus protons have a positive charge and significant mass as well. The mass of a proton is almost the same as a neutron. It's a little bit less. So that's the nucleus here. That's sort of the center part of an atom. And then this is surrounded by a cloud of electrons shown here. So electrons have a really, really tiny mass. It's almost negligible, but they have the equal and opposite charge to a proton. So if you have one proton and one electron, the charges balance out. You have no net charge. But if you have an excess of electrons, you'll have a negative ion. If you have an excess of protons, you'll have a positive ion. So when looking through the periodic table, you'll see entries that look like this. First, you'll have the element name, followed by its symbol. Each symbol is basically 1 or 2 letters that is used as a shorthand for the element. At the top here, you have the atomic number. This basically, every element has a unique number of protons. So the only element with 1 proton is hydrogen. So that's sort of a unique identifier here. And then down here you have the mass. So for hydrogen, there's 1 proton in the nucleus, there's 1 electron, and there's no neutrons. So it has an atomic mass of 1 mass unit. So we can compare this to the next entry on the periodic table, helium. So helium has 2 protons here, as identified by its atomic number, but it has a mass of 4. And this is telling us that there's 2 neutrons in the nucleus as well. So there's 2 neutrons, 2 protons, so it has a mass of 4. This mass scale, by the way, this atomic mass unit scale, or AMU, is really defined by the carbon nucleus. So carbon has 6 protons and 6 neutrons within it, and so that leads to an atomic mass that's defined as 12. All right, so this is you can see all the entries of the periodic table here. You can see the numbers, the atomic numbers increase. So 1 here, 2 here, and 3, 4, etc. So molecules gain protons as they move down and to the right in the periodic table. So there's two sort of key ways to view the periodic table, and that's through rows and columns. So a column is called a group, and it basically groups together elements with very similar chemical properties. So magnesium, calcium, strontium, these are all elements that that behave very similarly under a wide array of chemical conditions, and this leads to similar behaviors in the environment, for instance. So you may know that corals produce a shell of calcium carbonate as a coral skeleton. That's what builds coral reefs. But it's very easy, for instance, for magnesium to substitute into that crystal structure by displacing the calcium. The magnesium has very similar properties, and it can fit right in. Whereas going across the periodic table, so a row or a period, the chemical properties of each element are changing pretty dramatically. And this is because the number of valence electrons is changing here. So lithium has 1 valence electron, beryllium here has 2, and this increases all the way to the right. So just to define valence electrons, because it can be a bit tricky. So we already mentioned how you have an electron cloud that sort of orbits the nucleus, and this is where all the negative charge of an atom is stored, and all the positive charge is found in its nucleus. So you can split up the total electrons into all of the inner shells. So carbon has one inner shell here, and then one outer shell. This is called the valence electron. So a valence electron is considered full if it has 8 electrons within it. And so carbon here starts off with 4. And so in order to achieve a maximally stable 8 electrons in its valence state, it can find a way to basically gather 4 more electrons from its environment, or to give these up, and it can sort of knock back down a level and have the previous shell be full. And so this is a major driver of different types of chemical bonds that form. So the desire or the drive among different atoms to fill their electron shells sort of dictates what kind of chemical bonds are formed. So returning to the periodic table, we can go through a couple examples of how we can predict the type of chemical bonds that form based on where they fall on the periodic table. So first, we colored this into 2 groups. We have yellow here. All of these elements have unfilled electron shells and will participate in bonding to some degree. But in blue, you have these gases here called the noble gases. So this is helium, neon, argon, krypton, xenon. These are all elements that have a totally full electron shell. And so there's no reason for them to seek out bonds with other elements. They just exist as atoms flying through space in the gas phase. They don't interact with anything. So that's sort of where this idea that they're more noble, because they're kind of above the fray. Everyone else, though, is not above the fray, and so they're going to be doing their best to bond and get a full electron shell. So let's look at an example. Let's look at sea salt, which is sodium chloride. So sodium here is on the left-hand side of the periodic table. It's got 1 valence electron, whereas chlorine over here has almost a full shell. It's got 7 valence electrons. So you put chlorine and sodium in a room together. The abbreviation for sodium is Na, by the way, so it's a bit confusing, but Na is sodium. So you put these 2 atoms in a room together. What happens is the chlorine steals the extra electron from sodium, and everyone's happy. So sodium knocks back down to its lower electron shell, which is full, and chlorine completes its electron shell, and that's full. Because chlorine gains an electron, it has a negative charge, so it becomes a negative ion, and sodium loses an electron, so it has a positive charge. The number of protons hasn't changed, but the number of electrons has gone down. So you have a positive charge on sodium, negative on chlorine, and opposites attract, right? So sodium and chloride bond together and you form NaCl, which is also the chemical formula for table salt. So if you zoom into a grain of salt, you'll see something like this. This is sodium and chloride being bonded together here. You have chlorine here in purple, sodium here in green, and you can see that the way that this crystal is organized is so that all of the positive charges to be surrounded by negative charges and vice versa. This is basically what drives this ionic bonds, or bonds between ions, between positive ions and negative ions. And this is what's called electrostatic interaction, but it's basically the positive charges are attracted to the negative charges. And you can see this kind of cube here, correspond to what you might observe sort of macroscopically, or just if you look at some salt pretty closely, you'll see it basically forms a cube It's sort of reproducing this crystal structure on an atomic level on something you could see, with your own eye. Okay, so let's do another example here. Let's look at magnesium, which is 1 over from sodium, and let's think about how that might bond with chlorine. So magnesium here has 2 electrons to give up, but chlorine only wants 1. So what the result of this is that 2 chlorines will bond with 1 magnesium here. So magnesium will lose both of its electrons. It'll have a +2 charge, and you'll have 2 chlorine ions that result with each with a 1- charge. And so opposite attract again, you have formed magnesium chloride salt. All right, so one more example here, magnesium and oxygen. So we talked about how magnesium wants to lose 2 electrons, so to form this Mg2+ ion. And oxygen here wants to gain 2 electrons, so it completes its shell. So that drives the formation of magnesium oxide, which is one of the most abundant minerals in the Earth overall. So now we'll think about what happens when you don't have elements at the left-hand end and the right-hand end of the periodic table. Let's think about something that's pretty important to us, carbon. Carbon's one of the most abundant elements in our body, and so is oxygen. Carbon and oxygen bond together pretty frequently. And this is not through an ionic bond. What happens is essentially that carbon and oxygen share electrons to complete their valence shells. So here in green is a depiction of carbon. Here in blue is a depiction of oxygen. Oxygen has 6 valence electrons, it needs 2 more. Carbon has 4, so it needs 4 more. And so essentially what you'll have is 2 electrons being shared between each carbon and oxygen. And so now, if you look here at the molecule carbon dioxide, you have a full valence electron for all the atoms involved. So this is a stable molecule that is abundant in our environment. It's the driving force behind global warming and climate change in the past as well. And one of the reasons it's so stable is the fact that these electrons are shared, and basically all of these atoms have a full valence electron shell. Okay, so up to this point we've talked about what defines bonds between atoms to make a molecule. But now in order to understand whether those atoms are found in a solid phase or a liquid phase or a gaseous phase, we'll talk about intermolecular interactions. So interactions from one molecule between another one. So when you have a solid, everything is essentially bonded together. So you have these permanent bonds between different molecules. That's what makes a solid stand up. It doesn't ooze out everywhere. It doesn't take the shape of its container. A solid is solid because all the atoms are bonded together to form a molecule, and all the molecules are bonded together to form a solid. In contrast, you have these really intermittent bonds in a liquid. So if you have 2 molecules in a liquid, say water, what you'll see is, it's hard to see this actually, but what happens is that there's these very fleeting interactions from one water molecule to another water molecule. And these very fleeting interactions, they're not permanent, but they're important enough because they hold all of the molecules together. They stop them from flying off to space in every direction. And that's what defines the properties of a liquid. A liquid can flow because these bonds are not permanent. They reset in fractions of a second, but they're still holding things together. Meanwhile, in a gas phase, there's no force that's really interacting between different molecules. They're sort of flying around through space. They're hitting each other and ricocheting like ping pong balls, but there's no force that's really holding different molecules together. And so we'll talk about plasma in a second. And so solids tend to form when you have lower temperature. And temperature is basically an indicator for how fast or how much motion there is in any given molecule. So as the temperature goes up, molecules start to move around more, they want to spin, they start buzzing around, and it's really hard to maintain these solid, stable, permanent bonds as the molecules try to move more. So that's why once you reach a critical temperature, you have melting. So that solid turns into a liquid. So then the molecules can move around more, but they still have these kind of fleeting bonds. You increase the temperature even more, and even those short-lived bonds are not favored because the molecules have so much energy they just want to fly around through space. And so that's what happens during boiling. You go from a liquid to a gas, and now there's no more. Each molecule has too much energy that it can't be bothered to basically stop and bond with another atom. So if you take a gas and you keep heating it up, what you'll achieve is essentially a plasma. Plasmas are pretty rare on Earth, but they're not uncommon. So for instance, lightning is a plasma, the northern lights are a plasma, the sun is a big ball of plasma. So what distinguishes a plasma from a gas is the fact that there's so much energy here that it's really hard to keep all the electrons stuck to a certain nucleus, and they start to dissociate. So you have this sort of roving cloud of electrons, you have this roving cloud of basically gas molecules that are ionized and flying around through space. It's a unique condition, but it allows for sort of unique chemical reactions to occur in things like stars, and we'll learn how why that's important. So the last thing that I wanted to show is just another view of the periodic table, and this is the oceanographer's view of the periodic table. This is a profile or a slice of each element sort of in the North Pacific Ocean here. So you'll see here, instead of the normal atomic entry in the periodic table, you see here are these sort of curves, and so on the y-axis for each of these plots is depth. So it starts in the sea surface, and then this is the sea floor here. And then the x-axis is concentration. So that's the abundance of that element in that little packet of seawater. And what you see is there's some elements like sodium, right? A big part of sea salt. There's no variation in the water column. The top of the ocean is as salty as the bottom of the ocean, more or less. But that's not true for all the elements. And so what's really fun about this is that you can, by measuring some of these elements, you can learn about the history of that part of the ocean. Did it undergo some kind of geological reaction, or was there some event that led to the input of a certain element, or that took it out of seawater? Is there some kind of ecosystem process that's taking up certain nutrients and moving them around as the biosphere sort of moves or sinks? So these are really powerful tools to understand how the ocean works from a snapshot. And the key part here is you just need to know what drives the behavior of each element in the ocean. But one of the fun parts is that there's just these big differences here in this behavior. All right, so this video was really just about a review of the basics here. So we defined what elements, atoms, molecules, and ions are. We talked about how the elements are organized in the periodic table. And we've compared how different atoms can bond together to form molecules, either to form covalent bonds where electrons are shared, or ionic bonds where there's essentially an interaction between a positive and a negative charge, but the electrons aren't shared. And lastly, we reviewed how bonds from one molecule to another molecule can influence the state of matter. Solids are rigidly bonded together, liquids are weakly bonded together, and gases aren't bonded together at all. They're just flying around, ricocheting. So these are concepts that we'll keep revisiting throughout the semester, so it's important to just pause here and make sure that you're on board with this, and if not, reach out for help.